Hyperspectral images measure intensity of light as a function of space and wavelength. The availability of spectral profile at each spatial location is used in identification of various materials in a scene. An important application of hyperspectral images is to identify anomalous materials in the scene, which have spectral profiles very different from the background. When the material to be identified are present in trace quantities, they are modeled as anomalous pixels. The image shows an example of the deep water horizon oil spill, where the oil spills present in trace quantities can be modeled as anomalous pixels. The scene contains a total of 200 spatially sparse anomalous pixels of oil spill. Current anomaly detection algorithms require the complete hyperspectral cube to estimate the location of anomalies, a process that is wasteful and needs several expensive sensors. If we can remove the background spectrum, then fewer measurements will be needed to estimate the anomalies. A popular model for representing hyperspectral images is that of low rank and sparse components. The background spectrum, which is made of only a few materials, can be represented as a low rank component. The anomalies then are represented as spatially sparse component. This implies that if we can remove the contribution of low rank component, we can estimate the anomalies by sensing a spatially sparse signal for which we need very few measurements. We propose a novel two-stage sensing mechanism for this purpose. In the first stage, we estimate a low-rank subspace basis for the background material by acquiring a pure spectral measurements of a few random spatial locations in the scene. In the second stage, we take a few spatially multiplexed compressive measurements of the hyperspectral image. By taking a projection onto the complementary subspace, we obtain sparse signal which can then be recovered using various compressive sensing techniques. Our imager consists of an objective lens which images the scene onto a digital micromirror device. The DMD enables spatial selection and multiplexing, which enables us to obtain pure measurements as well as multiplex measurements of the scene. The light redirected from DMD is fed into a spectrometer which measures the intensity of light across various wavelengths. We now show results with our proposed imager and algorithm. We show results on detection of anomalies on real data. We performed anomaly detection with our proposed algorithm on the deep water horizon oil spill scene. 500 measurements were taken to estimate a rank 5 subspace for the background spectrum of water. 3000 spatially multiplex measurements were taken to estimate 200 anomalies of oil spill and have been marked in red in the right image. Notice that the location of detected anomalies coincide with the oil spill locations. Our algorithm estimates anomalies with 1/16 the dimension of the hyperspectral image. We performed anomaly detection with data obtained by the imager we built. The image on the left shows the scene we used for anomaly detection, which consists of printed text on paper. The grey pixels in the red circle consist of anomalies formed by placing a white LED behind a diffuser. The image on the right shows 10 anomalies marked in red estimated by obtaining 64 measurements for subspace estimate and 250 spatially multiplex measurements for estimating the outliers. Again, our algorithm very well estimates the anomalous pixels. We show spectral signatures at 3 different locations. Notice that the anomalous pixel has a distinct peak in blue wavelength region representing the white LED, which makes it an anomaly in the scene. Our second scene consists of a scene printed on a paper which is predominantly red. 4 pixels within the white circle were illuminated by a red laser. The red laser is indistinguishable from the background for the naked eye. The image on the right shows 4 anomalies marked in green estimated by obtaining 64 measurements for subspace estimate and 100 spatially multiplex measurements for estimating the anomalies. Our algorithm very well estimates the anomalies in the scene. we show different spectral signatures at 3 different locations. Notice that the anomalous pixel has a strong peak in the red region corresponding to the narrow band of laser light. Our method also outperforms other compressive sensing techniques which jointly recover a low rank and sparse matrix such as sparse and robust PCA. Image on the left shows the test image we used for characterizing the performance of various algorithms. We created the image by forcing the image to be low rank and sparse with 79 outliers. Finally, our algorithm outperforms the Reed-Joule detector in detecting anomalies. We artificially inserted 71 anomalous targets in hyperspectral image and performed anomaly detection with our proposed algorithm. The receiver operating characteristic curve plots true positives versus false positives. From the plot, it is evident that our method has a larger area under the curve than the RX detector. In conclusion, we propose a two-stage sensing mechanism to estimate anomalies in hyperspectral images. Simulations and real experiments show the superiority of our algorithm in terms of number of measurements needed and estimation accuracy. Thank you.